Ladies and gentlemen, it is my great pleasure to welcome you to the presentation on a stochastic design approach for iterative learning observers for the estimation of periodically recurring trajectories and disturbances. This contribution to the European Control Conference is co-authored with my colleagues Thomas Chevet, Thach, Dinh, Julien, Marzat, and Tarek, Raissi. At the beginning of this talk, let's talk about similarities and differences between iterative learning control and the design of iterative learning observers. Iterative learning controllers have been developed over the recent decades in such a way that they do not take into account information of tracking errors along the current execution of some given control task, that means along a trial, but it also takes into account information on tracking errors from previous executions of the same control tasks in order to enhance the tracking accuracy subsequently from one iteration to the next. This general idea will be used in the current presentation to design an iterative learning observer by taking into account not only information about the estimation error with respect to the measurable system output in one iteration, but also the corresponding errors from at least one previous trial. In such a way, we will talk afterwards about possible iterative learning observer structures and how to optimize the observer gains in a systematic manner by reducing the estimation error covariance. This strategy for reducing the estimation error covariance is inherited by a classical Kalman filter solution, and in such a way, the iterative learning observer can be split up into a prediction and an innovation stage. As a benchmark application scenario, we will consider the charging and discharging dynamics of a lithium-ion battery, which comprises the modeling of the system and numerical simulation results. First of all, let's have a look at a classical discrete time dynamic system model with time-varying parameters. This discrete time system model has a state vector xk, a disturbance input matrix ek, and W and V are additive zero-mean Gaussian noise processes, W denoting the process noise and V the corresponding measurement noise. All system matrices, the matrix A, the matrix E, and also the output matrix C, may be time-varying. This system model is augmented by an additive lumped error correction term delta in order to account for the consideration of a deterministic model mismatch between the actual system dynamics on the one hand and the corresponding assumed system model for the observer design, as it will also be discussed later on in the application scenario in this presentation. In the case that our system model contains nonlinearities, we perform a classical Taylor series-based linearization of both the system equation and also the output equation in the most recent state estimate denoted by x tilde in the same manner as it would be done by an extended Kalman filter approach. Now let's discuss about the possible structure of an iterative learning observer. As already mentioned in the beginning of this presentation, the iterative learning observer consists of a prediction stage on the one hand and an innovation stage on the other hand. In the prediction stage, both iterations, the old one and the current iteration, denoted by I and I+1, are combined in terms of updating the expected value of the estimated state variables. And at the same time, both stages, the old and also the current iteration, are also combined in the update of the predicted state covariance matrix. Here we have the estimated covariance matrix as the outcome of the previous innovation stage as the input, and the predicted covariance denoted by the superscript P as the corresponding output of the state prediction. A is the system matrix evaluated both in the previous and then the current trial for the corresponding state estimates. And the same also holds here for the disturbance input matrix, where we assume that we have independent process noise covariances in both subsequent iterations. Now, in order to perform the innovation, that means a measurement-based update of the corresponding predicted state information, we take into account the measured data, YM, at the old trial and also at the current trial, I+1. Using both measured data vectors, we can derive the corresponding deviations between the measurements and the prediction stage outcome or the predicted system outputs that can be computed by the linearized system model with the output matrix Ci and Ci+1 multiplied with the corresponding expected value vectors as the outcome of the previous prediction. Now our goal will be to optimize two gain matrices, a gain matrix H1 that is being used in order to weight the corresponding deviations in the old trial, and a matrix H2 that takes into account measurement deviations from the corresponding predicted outputs in the current trial. The corresponding innovation stage equations follow the same structure as the classical Kalman filter output equations in the innovation stage, where the superscript P, as denoted before, comprises the predicted values and the superscript E, the result of the innovation stage. In the first line, you can see the update for the old expected value vectors only on the basis of one weighting matrix, the weighting matrix taking into account only the corresponding output errors from the previous trial, while the current trial equation takes into account the old and also the new deviations, where the new deviations are expressed in such a way that the difference between the old and the current trial should be minimized from one iteration to the next. Now, what we can do additionally is we can also express the corresponding estimation error covariance matrix in terms of the deviations between the true system states, which are obviously unknown to the observer, and the corresponding results of the estimation stage with respect to the expected value vectors. This corresponding estimation error covariance matrix depends on both gain matrices H1 and H2, which are yet undefined. Now, our goal will be to minimize this expectation error covariance in such a way that we find a closed loop, closed form solution for the corresponding gain matrices H1 and H2. To perform this minimization, we write up the corresponding trace of the estimation error covariance matrix. And what you can see here is, according to the introduced matrix H tilde, which depends on both the matrices H1 and H2, we have an expression that contains terms that do not depend on the unknown gain matrices, which depend in a linear fashion on the unknown gain matrices, and finally also which depend in a quadratic manner on the unknown gain matrices. Therefore, a differentiation of this cost function with respect to both gain matrices, H1 and H2, and setting the corresponding derivatives to 0 leads to the necessary optimality conditions. Solving this necessary optimality conditions afterwards in a symbolic form for the unknown gain matrices leads to the result that is shown here in the lower part of the slide. A more detailed derivation can be found in the corresponding proceedings paper. Now let's have a look at an application scenario. The application scenario is state estimation for an equivalent circuit model of a lithium-ion battery. There we have a state of charge-dependent open circuit voltage and also all remaining parameters, the series resistance, also those two additional RC subcircuits with parameters that are the ohmic resistance and the corresponding capacities, depend again on the state of charge of the battery. Those RC subcircuits take into account dynamics with short and long time constants, which are basically caused by the transportation of charge carriers due to diffusion phenomena and also polarization effects. Writing up the corresponding continuous time system model with the state of charge dependent parameters for RS, CTS, RTS, CTL, and RTL, leads to the continuous time system model that you can see here in the lower part of the slide. The last line of the system model is an underlying fast linear control circuit that has the desired terminal current as the corresponding input, and the actual terminal current IT is considered as the fourth state variable of the system. The output equations of this system are, on the one hand, the measurable terminal current and an expression that depends on the terminal voltage of the battery in such a way that all constant offset terms have been subtracted from the corresponding output voltage VT in the corresponding model. Now, using Kirchhoff's voltage law, we end up with the corresponding expression depending on the open circuit voltage on both voltages VTS and VTL, and also on the voltage drop here that arises at the series resistance of the battery. This output equation can be reformulated in a symbolic manner in such a way that we end up with a quasi-linear representation. And this quasi-linear representation denotes here the state-dependent output matrix, which is being used in the extended Kalman filter-like innovation stage of the ILO. During the following simulation case study, we distinguish two cases. The first case will be that we assume that the true system model, which has been used to generate measured data by means of simulation, has an additive offset from the simulation model that is included in the ILO. Those deviations correspond to errors in the magnitude of around 0.02% with respect to the charging efficiency and up to 300% in the variation rates of the voltage with a larger time constant. In addition, in the case C2, we also have disturbed the entries of the system matrix AK by using uniformly distributed random numbers from the interval between 0 and 0.1. Now let's have a look at the corresponding simulation results for the case C1. There you can see in the very first iteration the result of a classical extended Kalman filter solution, which is also the initialization of the iterative learning observer. On the left-hand side, you see the estimation of the state of charge with the estimation error of the state of charge in the middle. Obviously, after the very first iteration, the iterative learning observer already has achieved to significantly reduce the estimation error for the state of charge. While for the voltage with a short time constant, we have practically vanishing estimation errors over the complete iteration and time horizon. For the voltage drop of the DRC subcircuit with a large time constant, we have a rapid reduction of the estimation error that is also being confirmed by the roots of the mean square error and the percentages of improvement of the estimates over the classical Kalman filter. There you see an improvement of up to 20% in those two state variables, the state of charge and the voltage with the large time constant, that have the significant estimation errors, while the other two are almost perfect also in the extended Kalman filter solution. The same statements are being confirmed for the case C2, where we also have a significant reduction of the estimation errors by using the ILO in the first and third state variable. Now, let's come to a conclusion. What you have seen is a derivation of a novel stochastic ILO procedure, which makes use of an optimization of the ILO gains in the same manner as it would be done by a Kalman filter approach. The visualization of the estimation accuracy has been performed by the charging and discharging dynamics of lithium-ion batteries. In future work, we will combine this approach with an ellipsoidal calculus to bound worst-case influence of nonlinearities and to extend the corresponding lumped disturbance model to further incorporate physical insight in the estimation process. Finally, fault detection and fault isolation approaches, as well as the inclusion of the ILO in a closed-loop control structure, will be further options for future work. Further related publications are summarized on this slide. Thanks a lot for your attention.